I've really been neglecting math, so we gotta do some math today. And honestly, not gonna lie, math is the most important of all the subjects. Even though it might not be that applicable to your job or whatever you want to do in the future, it's still the most useful because it develops your problem skills so much. It's amazing. Hello everybody, I'm Kara, and today we're going to be doing the 2016 AMC 12. A, by the way, A. Now personally, I think that AMC is one of those contests where if you have more time, you can always, guaranteed you're going to solve more problems. Because, it always takes you some amount of time to recognize the solution, but, once you recognize the solution, you get it. In physics, it's a lot more like either you know it or you don't, and just with most other Olympiads, you know it or you don't. But math is you just have to think about it for a long, long time, and you'll eventually get to it. Because math concepts, you generally know a lot of the math concepts, but I don't know, the problems are just super, super intense. So this is going to be kind of hard for me because even on normal time constraints, it's hard for me to get a super good score. But we'll see what we got, we'll try it out, and if it works, it works, if it doesn't, it doesn't. Let's do it. Alrighty, 75 minutes on the clock. And we start up right now. Okay, 11 factorial minus 10 factorial. Let's factor out the 10 factorial. We get 11 times 10 minus... that's 11 minus 1 over 9 factorial. And then you get 10 factorial. 10 times 11 minus 1, but there's 10 times 10, which is B, 100. Okay, B. Epic. And then 2, so 10 to the 2x times 10 to the 4x is equal to 10 to the 15, and then 6x is equal to 15, x is equal to 5 over 2. Wait, what? No, I'm trolling. This is just x. So, x is equal to 3. Alright, the remainder can be defined for all real numbers x and y. Oh, for real numbers, bro, okay. And then x over y, floor of that, and then what is the value of remainder? 3/8 minus 2/5. So we just plug it in, right? So 3/8 minus the plus 2/5, floor of 3/8 over negative 2/5. So that means that this would become floor of negative 15 over 16, which would floor to negative 1. So this would become negative 1, and then it would be 3/8 minus 2/5, and that would be 15 minus 16 over 40, which is negative 1 over 40, which is B. Okay. Alright, mean, median, and mode of 7 data values, 60, 100, x, 40, 50, 290 are all equal to x. Okay, so median, so let's do it in order. So 40, 50, how many numbers? 7 numbers, so it would be 60, x, 90, 100, 200. And we basically want the mode to be x. How do you make the mode? Okay, so would it have to be 60? Because then if 60 and 60 is also the median, would that work? Okay, let's test it. So 150 plus 390 is equal to 540, and then we do over plus 60. Did I add in the 60? No, I did not. So plus 60 is 600 over 7. No, that doesn't work, because then the mean would not be right. Hold up. So the first three sum to 150, then this sums to 390. So that's 540. And 540 plus x over 7 is equal to x, so 6x is equal to 540, so that means x is equal to 90. Oh, okay, yeah, we get up to 90. Okay, cool, 90. Alright, Goldbach's conjecture, I don't know what I don't like conceptual questions in AMC, that's not what I do AMC for, come on. Goldbach's conjecture states that every even integer greater than 2 can be written as a sum of 2 prime numbers. Okay. So far, no one has been able to prove that the conjecture is true, and no one has found a counterexample to show that the conjecture is false. What would a counterexample consist of? So basically, it does have to prove this is not true, so it has to be an even integer greater than 2 that cannot be written as a sum of 2 prime numbers. So, even integer greater than 2 that cannot... Yeah, okay, E. Alright, 16. A triangular array of 2016 coins has 1 in the... Okay, so 1 coin, 2, 3, and then... sum of the digits of n. Oh, so 2016. So we basically have that n times n plus 1 over 2 is equal to 2016. So that means that n times n plus 1 is equal to 403D. Okay, so this is a good example of when you should actually know the prime factorization of the year, because I do not know the prime factorization of the year, and this is going to take a lot longer. So basically, the approximate square root of this is what? So we could do square root of 40, so it should be around 60 something. So let's try 64, or 63. 63 sounds about right, so let's try 63 times 64. You would get 2, 1, 25, 0, 28139. So that would be 2312. Oh, what? Did I mess up? Oh, 37. Okay, so 0, 1, 4. Okay, so it is 63. So n is equal to 63, so that comes to 9. So that's a D. Which of the following describes the graph of x squared times x plus y plus 1 equals y squared times x plus y plus 1? Wait, what? So it's basically saying that x squared is equal to y squared, but you can't have that x plus y plus 1 is equal to 0. Because if it's equal to 0, then it's fine. So it is these, so this is x is equal to plus or minus y, so that's just like these two lines over here, and then and then x plus y plus 1 is also valid if that's equal to 0, so y is equal to negative x minus 1, so it would be another line over here. Okay, so it should be D. Nice, I love these questions, they're pretty legit. Okay, so let's draw this. Should be not too hard. Dude, geometry is my go-to. I love geometry. Alright, so this goes there, this goes there. Okay, not to scale, by the way. So basically, this is going to be like the midpoint, right? So the overall thing is 5 over 2. So this is 5 over 2. This is 3 over 2. Then there's a 1. Then there's a 1. And then this distance. Okay, I should draw this better. Hold up. We're going to have good diagrams, okay? We need them diagrams. Okay, so this goes here. This goes there. And then we could draw all these lines over here. Okay, so we know that this is 3 over 2. This is 1. This is 1. And then this is 8 over 2, so 4, this is 3, and then this is gonna be 4, and then this is 5 over 2, 3 over 2, 1, and then 1, 3, 4. Okay, now we just have a bunch of stuff. We could do that easily. So in this case, we're just gonna do the complement. So the overall area is 8 times 5 over 2, and then we subtract out these triangles, so 3 halves times 4, minus 3 halves times 4. And the reason I don't do 1/2 is because we have 2 of them, so it doesn't matter. And then we also have to subtract these triangles out too, so that would be 3 times 5 over 2. And then this should give us our answer, which should be 20 minus 6 minus 15 over 2, which is equal to 14 minus 15 over 2, which is equal to 13 over 2. Epic, which is equal to 6.5. So D. Oh no, we're getting too many D's. I don't like it. Unfortunate. Oh wait, I'm trolling. Wait, what? 8 times 5 over 2 is not... Wait. No, whoops. So this should be 8 times 5. Wait, that's going to be so off then. Okay, hold up. So this whole thing is 5 over 2, so this would be 3 over 2, that's right. Then 3 over 2 times 4. Okay, that is right. Oh, and then I have to subtract... Okay, so it should be 8 times 5 minus this whole thing. So it should be 40 minus 20. Okay, so this is how you do it. Yeah, because the 8 times 5 over 2 is this rectangle plus this rectangle, so this should work. So 20, which is the same thing. Okay, D. Okay, 5 small shaded squares inside of the unit square are congruent and have disjoint interiors. The midpoint of each side of the middle square coincides with one of the vertices of the 4 small squares. Okay, common. Okay, so they all have the same. Okay, so let's just draw it. Okay, theoretically on the actual thing, I would not have to draw these diagrams. That would be so much easier, but what? Oh my god, this is so disgusting. Whoops. Wait, so this whole thing is a unit square. So we could write that this is s root 2, then this is s root 2 over 2, and then this is another s root 2 over 2, and then this would go all the way over here, which is s root 2. So basically s root 2. So this is like a 45, 45, 90 triangle over here. There's a 90-degree angle. So we could say that this whole side length times root 2 is equal to 1. So we get that s times root 2 times 3 over 2 is equal to 1, and then we get that, wait, no, why is that not valid? Oh, this is just s over 2, it's not s over 2 root 2. So this would be s over 2, and then this would be, instead of that, would be s times root 2 plus 1 over 2 is equal to 1. So if we just divide it out, we should get our answer. So we get that s is equal to 2 over root 2, 2 root 2, plus 1. And then if we fix the radical nonsense, we get 4 root 2 minus 2 over 8 minus 1 is 7. So we get 4 root 2 minus 2 over 7. Wait, what? Hold up. So root 2, that's right. Okay. Then plus 1. Oh, we had to do this whole thing times root 2 again. So then we divide this by root 2 to get our answer. So if we divide this by root 2, this becomes 4 minus root 2 over 7. Okay, so now we get 4, 7, 4 plus 7 is E, 11. Alrighty. 5 friends sat in a movie theater containing 5 seats. Okay, so left to right is from the point of view of them. During the movie, Ada went in the lobby. When she returned, she found that they moved 2 seats, blah, blah, blah. Okay, so this is a logic problem, I'm assuming. So 1, 2, 3, 4, 5. Okay, so Bea moved 2 seats to the right. Ceci moved 1 seat to the left. D and Eddie moved, switch seat. Okay, so basically, Ceci either moves left into Bea's seat, or she moves left into Ada's previous seat. So, oh, it's an N seat for Ada. So Ada ends up with an N seat. Well, basically, Ada's either going to go into Ceci's old spot or her own old spot. So in order for her to go, okay, let's try this. So let's say that Bessie's over here, or dude, Yusuko has too much of a toll on me. Come on. So this is over here. She goes over there. Ceci could be here. And then, okay, well that doesn't work because we want to have one of the end seats open. So we know that D and Eddie, so D is going to be here, let's say, and then B is there, and then C is here, and then E is here. So these two guys switch. No, but that's not okay because B got to have an open spot. Okay, what happens if, wait, A doesn't have to start on the end though. Oh, we could do it backwards, right? So A, okay, so this is at the very end. Let's start from the end. And then Bea moves 2 seats to the left from the end, if we're going from end to the beginning. So Bea's have one of these seats, and then let's say that she's here. No, let's say that she's here, and then we know that Ceci moves one to the right, basically, if we do opposites. And then we know that D and E could just be here. So this is the end configuration. So if we want to get the original configuration, we just undo everything. So B moves to the left. So B is over here, this guy moves to the right to that blank, to C, and then E and D. Alrighty, so it got to be this person, so second, B. Oh nice, a pie problem. Okay, so each of the 100 students in a certain summer camp can either sing, dance, or act, okay. Some of them have more than one talent, but no students have all 3, okay. There are 42 students that cannot sing, 65 that cannot dance, and 29 that cannot act. How many students have 2 of these talents? Okay, so we could draw our Venn diagrams. Bro. Okay, so we have Venn diagram, Venn diagram, Venn diagram. Okay, so basically, so at least they all fit into one of these categories. So if they can't sing, so let's say this is sing, this is dance, this is act. So if they can't sing, they're in like one of this areas. Okay, so that's 65. That's 42, and then 65 cannot dance, so that would be all here, and then 29 would be all here. So if we want 2 of the talents, we have to do like right here and right here. So we know there's 0 in the middle. So we know that if we add up like this plus this, okay, wait, let's do it nicely. So this, we add up this region, okay, and then we add up this region, and then we add up this region. So you see that like each of the ones that only have one ability is counted twice, but like the double abilities are only counted once. So if we want to have the double abilities, we gotta add them. So 42 plus 65, 29. Alright. And then if we subtract 100 times 2, we're gonna take out like the desired amount twice, and we'll have negative of our double thing. Okay, so let's just do that. I don't know, that was a good explanation, but so basically you count this one twice, you count this one twice, you count this one twice. But you only count this one once and this one once, right? So if you subtract 100 once, you're left with 1, 1, 1. But you don't want those, you want these ones over here. So if you subtract another time, you're going to get 0 of these ones and then negative 1 of all these. And then you take the negative of that and you're good. So 107 plus 25 is 132 minus 200 is equal to negative 68. So 60, oh, nope, that's wrong. Oh, 29. So then this would be, plus 29 would be 136, so that would be 64. Okay, so E. Alrighty, problem 12, let's do it. How much time do we have? We spent, okay, doing good. So, problem 12 would be, in ABC, we have BC is equal to 6, CA is equal to 8, and BC is equal to 7. Okay, and then point D is on BC, AD, okay, so angle bisector. Point E is also an angle bisector, they intersect at F. So what's the ratio of AF to F? Okay, so this is not too hard. You just use angle bisector theorem like 600 times. That's what you do whenever you have angle bisectors. Okay, so this over here, BC is equal to 7, AB is 6, and then this is 8. So if we use angle bisector theorem on this side, we basically get that this is 7 times 8 over 14, and then this is 7 times 6 over 14. This ratio to this ratio is just this side over this side, which is just 7 over 14, which is 1 to 2. Or 2 to 1 in this case. So C. Alright, n be a positive multiple of 5? Okay. Problem 13. 1 red ball and n green balls are arranged in a line in random order. Let P of n be the probability that at least 3/5 of the green ball are on the same side of the red ball. Observe that P of 5 is equal to 1, and that P of n approaches 4/5 as n grows large. What is the sum of the digits of the least value of n such that P of n is equal less than 321 over 400? So the best way to do this is to find a closed form for it. So how are we going to do that? So basically every ordering is going to have an equal probability. So we just have to find the orderings where 3/5 of the balls are on the same side of the red. So what we could literally just do is let's say we just put 3/5 of the balls on one side. So this is 3/5 n. And then there's a red ball, and then there's the rest of the green balls. Or no, we haven't put them down yet. So we're guaranteed that we have 3/5 n on this side. And then we had to put the remaining 2/5 n balls on either side of this. So this is like basically just stars and bars. You have 2/5 n balls to place, and you have one divider. So it's just going to be 2/5 n plus 1, choose 1. So that's just equal to 2/5 n plus 1. And then the total number of orderings is basically just going to be n, because you have n indistinguishable balls, and you have one divider. Oh, so it'd be n plus 1. Alright, so we want this to be less than 321 over 400. Okay, but you also multiply this by 2 because this 3/5 n could be on this side as well. So we know that this is basically equal to 4/5 n plus 2 over n plus 1, and then once n is equal to when n is equal to 400, this is 302 over 401. Oh, 322 over 401. So this is slightly bigger than 321 over 400, because if you think about it, 2/4 is slightly less than 3/5. So that means that the next n, we could just assume that that's going to be smaller than this over here. So our n should be just 400, right? Or well, let's just try it. Let's see, 405, would that work? So it'd be 405, 81 times 4, 324 plus 2, so 326 over 406. So that's smaller than that? Wait, there's literally no way. Well, anyway, 400 is not right. But we have our thing here. Oh wait, let's try dividing it out. Okay. So this is also equal to 4/5 plus what? Plus 6/5 over n plus 1. So what is 321 over 400 minus 4/5? Okay, let's erase all this nonsense. Alright, so 321 over 400 minus 4/5. Oh, and we also know this is correct because it says that it approaches 4/5. So we subtract 4/5. And then this is times 80, so it's just equal to 1 over 400. So we want 6/5 over n plus 1 to be less than 1 over 400. So if we multiply this out, we get 6 over n plus 1 is equal to 1 over 80, which is equal to 1 over n plus 1 is equal to 1 over 480. And that basically means that n has to be equal to 479. So that basically means that at 479, P of n is equal to 321 over 400. However, if we want it to be less than it, we just add 1, so it would be 480, so that would be A. Alright, problem 14. Each vertex in a cube is to be labeled with an integer from 1 through 8, with each integer being used once. Alright, in such a way that the sum of the four numbers on the vertices of a face is the same for each face. Okay, arrangement that can be obtained from each other through rotations of the cube are considered the same. How many different arrangements are possible? Okay, so what is 8 factorial even? So 8 factorial is equal to 720 times 56. Ew, that's massive. Fine. What's the, how many faces are there? But actually some of the numbers are reused, right? So each number is used in 3 faces because there's 3 faces around a vertex. So that means it's basically just going to be 8 factorial cubed is the total. And if we want to find out what it is per face, we just take the, 6th root, no, how many faces are there? Yeah, 6th root of this. So it's basically 8 factorial square root of that, and that's going to be the product of each face, what it has to be. So 8 factorial is equal to 8 times 7 times 6 times 5 times 4, wait, no. This is wrong, hold up. Oh, sum, whoops, not product, bruh. Okay, so the product's going to be 8, 1 plus, no, it's the n, okay, so it's going to be 8 times 9 over 2, so that's the sum of 1 through 8. And then we're going to multiply it by 3 because each vertex is part of 3 faces, and then if we want it per face, we have to divide by 6. So it's going to be 72 over 4, which is just 18. So each face has to sum to 18, alright? I mean, we probably could have just figured that out because 1 plus 8 is 9, and then you have 4, so 9 times 2 would be 18. So I guess we got 18, alright. Then how do you do this? So you could, well, let's draw it, okay. Alright, so let's just say we fix 1 here. And if we fix 1, then we don't have to care about all this rotation. No, actually we do, because it might be rotated around the 1, and that would be considered the same. But yeah, whatever, we could fix that later. Alright, let's just say we did like 1, 2, 7, 8. Alright. Now, do we have a guaranteed... Oh, no. Wait, is that even possible? Wait, no, 1 and 2 can't be next to each other. That's illegal. So, 1, 8, 2, 7. Okay. So in this case, will we have a solution? So let's try to find a solution. Let's see. Maybe if this was 6... Okay, so this sums to 10, so we need 8 more. So we could do 5 and 3. Try 5, 3. And then if this is 7, 2, 5, that's 14, and then you need a 4 here. And then the bottom would be 1, would be 9, 3... What's the last one, Marine? 6. So does this work? 1, 8... Okay, that works. Alright, 1, 7, 6, 4, that works. Alright, so this is one solution. Are there any other solutions? Because I didn't see any other options, right? So we had 1, 8, 7, 2, and then we tried putting stuff on, but I don't think... Okay, let's try it. So we put 5 first, right? Just randomly put a 5 on. Why don't we put a 4 next to the 2? Alright, then this has to be 5, and then this would be 14, so this... Wait, what? Okay, so this doesn't work, because you can't have 14, and then this would have to be a 4 too, so that doesn't work. Huh, I feel like I'm missing something. Well, I mean, I'm for sure missing something, because otherwise it'd be solved already. Let's see. Okay, so 4 doesn't work here. Let's try 6 maybe. So that's 8, this is 7, so this would be 3, then this would be, what? So 8 plus 2 plus 6 is equal to, so this would, no, we can't do that either. So basically 8, 2, and 4 can't be on the same face. Alright, because if you do 8, 2, 4, then you need another 4. If you do 8, 2, 6, you need another 2, so that doesn't work. Alright, so what's the last thing we could do? We could do a 3. Let's try that. Alright, so 7 plus 2 plus 3 is 12. So this would have to be a 6, and then this would have to be an 8 plus 13. That would be a 5, and then this would be a 4. Would that work? Yeah, that would work. Okay. So we have 2 options for this top face of the thing. And I'm assuming that is always going to be 2 no matter what this top face is. So let's just find all the valid top faces. So 1, 7, 8, 2 works. Well, then we did 1... Okay, so 2 can't go here. One of them we did 3. So then the other edge would have to sum to 14, which we could do as 9, 5, and... No, what? 8, 6, and nothing else. So that doesn't work. Alright, I think I'm spending way too much time on this one. We could figure it out later. Okay. Not ideal. Okay, we'll come back to it. Alright, circles with PQ and R on the same side as L and are tangent to L, P prime, Q prime, R prime. Okay. Okay, so basically have this, and then you have P, Q, whoops, they're tangent, and then R. Boom. And then this is R prime, and this is Q prime, and then this is P prime. And this is 1, this is 2, and this is 3. And I think for the area of triangle PQR. Okay, so this looks like it's on a line, but I guess it's not. Okay. Wait up. Hold up. So this is perpendicular because they're tangent to the line, right? Yeah, they're tangent to the line, so these are all perpendicular. So why can't we literally just find the area of this trapezoid and then subtract from these 2 trapezoids? Yeah, I think that's the intended solution. So basically you have to find these 2 distances. So how do we do that? So we know this is 2, this is 1. And then this is 1, like if we do a line here, this would be 1, and then it'd be 3 squared minus, so this would be 2 root 2. Alright, and then same thing for this. If you draw this line, this would be a 1 here, and then this would be a 3 plus 2, so this would be 5, so it would be 25 minus 1 is 24, which is 2 root 6. So this is 2 root 6 over here. So basically the area of this big trapezoid is going to be for 2 times 2 root 2 plus 2 root 6. Alright, and then we subtract this first trapezoid, which is going to be 1 plus 2 over 2, which is 3/2, times 2 root 2. And then we're going to subtract this trapezoid over here, which is 3 plus 2, 5 over 2, times 2 root 6. So this is basically just going to be root 2 minus, no. So this is going to be 5 over 2 root 2. Oh, no, wait, I'm trolling. Hold up. So it would be root 2 minus 5 root 6. Minus root 6? No, that's negative. Hold up. Oh, maybe, yeah. I guess we just got it backwards. So I guess it'd be root 6 minus root 2. Yeah, root 6 minus root 2. That makes more sense. So basically the diagram's wrong. The diagram should be like this. Okay. Yeah, that makes sense. Alright, so D. Alright, so you got log 3 of x, log x of 3, and then you got log 1/3 of x, and then y equals log x of 1/3. Alright, so first off, you know that like a log graph basically looks like this. So when x is equal to very negative numbers, then, or x just can't equal negative. So this is a log graph, okay? So this is how y equals log 3 of x is gonna look. This last one, sorry, log 1/3 of x is basically just a negative of that, like it goes the other way, I think. Yeah, that's the opposite way. Okay, and then the other ones is gonna be log x of 3. So that basically means as x is like small, then you have to have more of a power to get to 3. Or more of a negative power, wait, what? Yeah, so it's like this kind of. Oh wait, but it's not defined for negative numbers. Okay, let's see. So if we take e to the y, or like 10 to the y, so we get 10 to the y, or no, x to the y. Wait, what? Hold up. Huh, this other graph looks weird. Well, so we know that this is an intersection point. What do we do about the other two graphs? I don't know how to do those. So as it gets more x, then you're gonna have like closer and closer to 0. But as you get a smaller x, it's gonna go negative, negative, negative. But originally it's positive. Okay, so it's like kind of like, when does it intersect 0? So when is y equal to 0? So y is equal to 0, well, never, I guess. Because when log of something is 0, the answer is equal to 1. No. Because when you have log x of something, it's only equal to 0 when the thing is equal to 1. So that's not going to work. So it just never intersects the y-axis. So how does that make sense? Bruh. Oh, so it is negative and small ones. Wait, I'm so confused. So, if it's negative, so if x is small, then you're gonna have to have a negative power to get it to 3. Okay, but as x gets really big, you're gonna have to have a positive but small power to get it. So, is it just not a continuous function? Hold up. Okay, I think we can't spend too much time on this. I don't know whether I'm gonna get that one. Okay, let's try 17. Alrighty, ABCD is a square, and then you have equilateral triangles that are exterior to the square. Okay, this shouldn't be hard at all. Okay, I know how to do this one. Okay, so it's like this. Epic. So now the way you do this kind of problem is you basically just find this length over here in terms of the side length of the square. So let's say the side length of the square is just 2, then this would be 1, and then this would be 1 over root 3. Okay? So now you have the side length of this new square is going to be 1/2 plus 1 over root 3 times root 2. So this is the new side length of the square. And it's asking for the ratio of the area. So we basically get that this is root 2 over 2 plus root 6 over 3. And then you want to square this in order to get the ratio of the area. And that's just going to be 1/2 plus 2/3, and then plus root 2 root 3 over 3. And then if we simplify this, we should get a nice answer. So we get 3 plus 4, 7 over 6, plus 2 root 3 over 3. Which is not right. Hold up. So this, oh wait, we said the side length of the square, so we had to divide by 4. No, but even then, that's just wrong. So, okay, well, so let us say that the side length of our square is equal to 1, so that's easier to understand. Okay, so side length of our square is 1, so this would be 1/2, and then this would be 1 over 2 root 3. So the side length of our new square is going to be 1/2 plus 1 over 2 root 3 times root 2, and then this whole thing squared is going to give it the ratio of the areas. So it's just 2 times 1/4 plus 1 over 2 root 3 plus 1 over 12. And that is just equal to what? So 1/4 plus 1/12 is equal to 4 over 12, which is 1/3. And then you add 1 over 2 root 3, and then you multiply by 2, so you get 2/3 plus root 3 over 3, which is equal to 2 plus root 3 over 3, which is B. Nice, okay. So we skip another one. Whoops, I'm skipping a lot. Okay. Alrighty, for some positive integer n, the number 110 n cubed has 110 positive integer dividers, including 1 in the number 110 n cubed. How many positive integer dividers does the number 81 n to the 4th have? Okay. So basically you have 2 times 5 times 11 as your prime factorization times like P1, 381, blah blah blah, P2, 382. So this P1, A1 stuff is like prime factorization of n. And cubed makes it 3 alpha 1. Okay? And then this has 100. So we basically have that 2 times. We basically have 2 times 2 times 2. If you use the prime factor formula, like how many factors the thing has based on its prime factorization, then you get 2 times 2 times 2 times 3 alpha 1 plus 1 times 3 alpha 2 plus 2, and so on. And in the other case, we have 3 to the 4 times P1 4 alpha 1 dot dot dot. So that would be 5 times 4 alpha 1 plus 1, so on and so forth. Okay, wait, how did that work? 110 is divided by 10 to get 11. So 2 times 5, oh, bruh. Okay, so basically this is not necessarily true. Hold up. Because P1 and P2 could be 2 or 5 or 11, and I think they have to be. So in order to get a 110 positive integer divisors, you have to have 2 times 5 times 10, 11. So if you want to find P1, then P1 is going to have to be, that works, okay. So in order to get 2 times 5 times 11 positive integer divisors, you have to make this 2 to the 1, then 5 to the 4, and then 11 to the 10. So in that case, n is equal to 5 to the 3 times 11 to the 9. Okay. So if we want to find how many there are in 81 n to the 4th, we could just do that. So it'd be 3 to the 4. Oh wait, and then we had to divide by 3 because we have 3 alpha 1 and we want to find actual n. So this would be 1 and this would be 3. Okay, so if we multiply to the 4th power, then we have something interesting, because then we have 3 to the 4th times 5 to the 4th times 11 to the 12th. So that's just 5 times 5 times 13, which is 25 times 13, which is equal to what? It's equal to 325, which is D. Nice. How much time we get? Okay, 28 minutes. Alright, Jerry starts at 0 on the real number line. He tosses a fair coin 8 times. He gets heads, he moves 1 unit in the positive direction. He gets tails, he moves 1 unit in the negative direction. Probability that he reaches 4 at some time during this process is A over B, where A and B are relatively prime integers. So in order to get a 4, you can either go 4 heads, 4 tails, get 5 heads and 1 tail, or 6 heads and 2 tails. Okay, let's do casework, that'll be fun. Okay, so 4 heads, 4 tails. So in order for this to work, it's basically, so there's a 1/2 to the 8th probability that this happens, times 8 choose 4. No, we don't want to, we want to find the number of ways that are valid. So the total number would be 8 times 8 choose 4. Actually, no. We just want to find the probability, so we don't need this. Okay. So now we have to find the ways that you can do 4 heads and 4 tails such that you reach 4. The only way to do that is if you do 4 heads first and then followed by 4 tails. So there's just going to be one way for that. So this is all we got. Times 1. Okay, now we got 5 heads, 3 tails. So now you can either have 4 heads followed by a tail, or you can have like this 1 tail like anywhere in between. Because you could have like 1 head and 1 tail, so you go back, but then you have 4 heads in a row. As long as you have as long as you don't have 2 tails before your last head. So, let's see. So, we could either have T, H, 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 T, T. Then you could have this goes here, this goes here, this goes here, this goes here, and this goes there. Okay, so that's 1, 2, 3, 4, 5, 6. So 6 ways. Alright, 6 heads, 3 tails. No, 2 tails. So now in this case, it doesn't even matter where the tails are, because you have 4 more heads than you do have tails. So then you could just take any order of this. So there's 8 choose 2. And then if you have 7 heads and 1 tail, then that's guaranteed as well. So then you have plus 8. And then if you have all 8 heads, that also works. So that's 1. So we basically have 1 plus 6 plus 8 choose 2, which is 28, plus 8 plus 1, all over 2 to the 8. Alright, and then once we do that, we could just solve this. So this is 7 plus 9 is 16 plus 28 is 48, or 44. Wait, what? So we get 44 over 2 to the 8, and then that's 11 over 2 to the 6, which is 11 over 64, which is 75, is not right. Okay, so there's 1, right? That's for sure 1 for this case, right? We could have t goes in between, no. Alright, then 5, the t could go anywhere, so it could either be the first position, second, third, 4th, 5th, 6th. Alright, that's 6. And then 6 choose 2, no matter where you do it, it'll be fine. So 8 choose 2, and then 7 heads and 1 tail is guaranteed, so that's 8, and then there's 1. 36 plus 6 plus 2 is 44. What? Oh, wait, okay, so the other one is also if, once you reach 4, it's fine. So, if you put, 4 heads, then it doesn't matter how you orient the rest of the stuff. So you could either have, 2 tails and then a head and then a tail, or you could have 3 tails and then a head. So the last head could be anywhere, it doesn't really matter. Okay, so we had to add these two in. So then we have 46 over 2 to the 8. 46 over 2 to the 8 is equal to 23 over 127, or 128. And then this should be 151, which is B. Nice, let's go. Alrighty, number 20. So a binary operation has the properties that A of this thing, so it's basically associative, kind of? Oh, not really. Okay, so what could we do? Alright, so basically it says that 2016, this, fix, this, x is equal to 100. Which is basically the same thing as saying that 2016, this of 6 times c times x is equal to 100. So if we could theoretically like make 2016 like multiply by itself, then we'd be chilling. Oh wait, so we also know that like a of this b is equal to a this b this c this over c. Okay, so 2016 6, so this would be 2016 times 6 of c over c. So we made c 6, then we get that 2016 of 1. Well, then we get that this is equal to this, right? Oh, over 6. How can we get this to multiply by itself? Because unless we get it to multiply by itself, we can't figure out how to get the 2016 work. Wait up. What happened that we treated it the other way? So we treated like this whole thing as b. Then we get that 2016 times this whole thing times this, and then this, and then we can multiply it by something. Oh wait, a geometry problem. We're doing that first. Hold up. Okay, so we have a quadrilateral. Okay, so we have a circle. We have a radius 200 root 2. We have a quadrilateral with 200, 200, 200, and then nice. Okay. Actually, that's not to scale. 200 should be smaller. So it's 200, 200, 200, and then we want to find the last side. Okay. So why don't we try finding theta using law of cosines? We basically get that 200 root 2 squared, which is just 2 times 200 squared times 2, is equal to, or no, minus. Oh wait, the formula is 2 times this times 1 minus cosine theta is equal to 200 squared. So we divide out the 200 squared, we basically have 4 minus 4 cosine theta is equal to 1. And then we basically get that cosine theta is equal to 3/4. And now we just have to find cosine 3 theta. Okay. So cosine 2 theta is just 2 times this squared minus 1, which would be 9 over 8 minus 1 is equal to 1/8. So that is equal to cosine 2 theta, and then if we do that again, we had to do cosine 2 theta plus theta, I guess, yeah. And then that's just equal to cosine 2 theta minus sine 2 theta, sine theta. Alright, so cosine 2 theta we got as 1/8, cosine theta 3/4, and then sine 2 theta just root 63 over 8, and then the other one would just be you square this, you get 9 over 16, 7 over 6, root 7 over 4, and then this is just 3 over 32 minus 21 over 32 is equal to negative of this, negative 9 over 16. So this whole thing is negative 9 over 16, so if we just plug it back into this, we get 1 plus 9 over 16 is 25 over 16 times 2 times 2 times 200 squared, and then we take the root of that to get our final answer, and we get 2 times 200 times 5 over 4, which is just equal to 500. Hey, very nice. E. Oh, August. LCMs. Okay, whatever, let's try it. Alright, so you basically have X, Y, have a 72 LCM, 600 LCM, okay. I kind of don't want to do this. Let's see, what else do we have here? Okay, why don't we just stick with what we missed earlier, so we're going to go back to 14. Or let's go to 16, I think 16 is easier. So basically we can set these equal to each other. So log 3 of x is equal to log 1/3 of x, and then this you just do like 3 to the whatever, and then you get that x is equal to negative x. So that's only true when x is equal to 0. So they do intersect. So these two intersect. Let's try another pair. So that's 1. Alright, log 3 of x and equal to log x of 3. Okay, so should we just do... What's better? Is it better to get rid of the x on this side or the x on this? Why don't we try this? X log 3 of x is equal to 3. Okay. Well, literally when x is equal to 3, this works. But I don't know how to make it easier to solve. So this at least intersects once. I'm assuming it intersects once as well, because I don't think the shape is right. Okay, let's try this analysis one more time. So as x gets bigger, you're going to need a negative power. No, you're going to need a positive power to make it into 3. However, as x gets really small, it's going to have a negative power. However, and it does intersect. Oh wait, no, I'm analyzing the wrong one. Okay, so as x gets bigger, you're gonna need, wait, what? So as x gets bigger, you're gonna have a smaller and smaller fraction. But as x gets smaller, you're gonna have a negative factor. It's not gonna, what? But it never crosses 0. How did that even happen? Well, let's see what happens as it approaches 0. Or as it approaches 1. So as it approaches 1, you're gonna have less and less of a negative, or more and more of a negative. Or you're gonna have more and more of a negative. So basically the graph of this one is, and then as you're right past 1, you're gonna need even more and more. You're gonna have a really positive, and then it's gonna, okay, so we finally figured it out. So this is how the graph looks. There's like a thing going down that way, and then there's a thing going like that. Oh no, sorry, a thing going like that. So this part is gonna intersect with both of the first ones. Wait, what about the 1/3 one? So the 1/3 as x is 0, or close to 0, is going to have a very positive. Oh, wait, what? Oh, there's like a, holy moly, so it never goes positive here, so it goes like that. Huh. Okay, now I'm just trolling. Well, something like this. Anyways, that's somewhat how it looks. Wait, how much time do we have left? I think we're out, basically. Okay. So it basically goes like that. Well, basically that's saying that x to the y is equal to 3. So as x gets really small, as x gets really close to 0, then y has to be very, very negative. No, it has to be slightly negative. So it'll get really close to 0. Okay. But it never actually hits. Okay. So it is something like that. So one of them go like this, is going to hit it twice. This top one is only going to hit the top one. So we have to add in 2. And then, so this is between these two. And then between this one and this one, it's going to be not going to hit this one, but it is going to hit that one. So that's 1. Alright, so that's 3 possibilities we've handled. But then what happens about the... Okay, so then the other one is going to be x is small. Okay, I don't know how to do this one. Okay, whatever. No. Can we do 14 in the remaining time? I don't think so, honestly. Okay, I think my time management for this one is bad, so not going to do great, but it's okay. Alright, so we got to have 18, so 1... 2 doesn't work, 3 doesn't work, 4 does not work, so that could be 8 and 5, and then, so this would have to be 8, 5, and then this one would have to be something else that sums to 13, which is 7, 6. Alright, so now we have that out of the way. So 1, 5, 6 is 12, but that doesn't work, so this is not going to work here. Could you do 6, 7, does that work? 1, 5, 7, you get 13, that doesn't work. Alright, let's try flipping it. 8, 5, and then 6, 7. Alright, so this is 16, this would be 2, then this is 15, this would be 3, and then the last one would be, oh yeah, okay, that's right. Okay, so this would be 5, 6, 11, wait, what? Hold up. Oh, 7 is the one in the back, okay, that works. Nice. So that's 1, but then this could flip with that, so that's 2 ways, and then let's try this is 5, and then the remaining could either be 6 or, wait, what? So 16, so that's sum to 12, so it could either be 7 and 5 or 8 and 4. But that doesn't work, so you can't have 7 and 5 because 7 and 5 is already used, so 6. Then it's, what is it, 7? So you need 11, so it'd be 6 and 5, no, 7 and 4, so 7 and 4 might work. And then, what's the other one? 8 and 3. So we know that 3 can't be next to the 1, so 8 and 3. Okay, whoops, 8 has to be next. Alright, so after we're done with this, if this works, then we're done. Okay, so 15, 16, 2. Alright, 7, 4, 11, 13, 13, 5. Okay, so this should work. Okay, so this works. So this is another 2. So it should just be 4, right? Oh, 4 is not even an answer choice. Do we count this some other time? Well, no, because we always had like 4 next to. Okay, yeah, whatever. This is all we got. Let's check our answers. So I only answered 18. So the highest I could get is what? 108 plus how many is remaining? So 18 minus, so 7 times 1.5. So the highest I could get is 118.5. Not great. Let's assume I didn't make silly mistakes, which is a very bad thing to assume, not gonna lie. Alright, so BCB, DED, DD, EBEC, ACDD, okay, BDB, AEA. Holy moly, we got all the ones that we did right, so 118.5, very nice. Okay, that's pretty bad, not gonna lie. Okay, so, things that I did wrong is because I didn't manage my time very well. I spent a lot of time on things that I probably should have gotten right, and I didn't actually solve them, which is a pretty bad idea. Okay, the way you have to do it, you have to balance whether or not you're going to solve it, whether or not it's worth the time. And I feel like those problems should have been worth the time, but it's hard to like talk and like think and all at the same time, so I don't know. Yeah, whatever. Maybe I'll downgrade to an AMC 10 because like AMC 12, even when I'm just going at my own pace, like without explaining it, like I still get like 130.5 or whatever. But AMC 10, I think I could do a better job of explaining, so we'll try that. Alright, thank you guys for watching. I hope you guys enjoyed. If this was helpful, let me know, and if you want more, let me know as well. As always, if you enjoyed the video, leave a like and subscribe for more. Thank you guys for watching again, and see you guys next time.